Today we'll discuss about Routh harvest criteria. First we'll discuss about what we mean by stability. Stability of the definition. There are different types of the stability, whether the system is stable, unstable, or the marginally stable. A system is stable if the natural response approaches zero as the time approaches to infinity. That type of system is called as a stable system. Then unstable system if the natural response approaches to infinity as time approaches to infinity. Then a system is marginally stable if the natural response neither decay or the nor growth but remains constant or oscillates. That type of system is called as a marginally stable. Then BIBO, bounded input, bounded output. The system is stable if every system is having bounded input and the bounded output. A system is unstable if any bounded input yields an unbounded output. A system stability definition, if we'll consider the any system, for example, for a bounded input which yields to the bounded output, that is called as the stability of the system. Or the system is called as a stable system. Here it is R of s is equal to 1 upon s, and the G of s is, here it is 3 divided by s into bracket s plus 1 in another bracket s plus 2. And here it is unity feedback is connected. Based on this, we have calculated poles and the zeros, and we have marked the poles and zeros. From this we can say that the stable system have poles only in the left hand of the plane. Then the type of system is called as the stable system. Then unstable system have at least one pole in the right hand side, so the type of system is called as unstable system. Here it is, in the unstable system, time approaches to infinity, the natural response approaches to the infinity. Then we will discuss different types of the stability or the different stabilities, absolute stability and the relative stability. As its name implies, absolute stability is the qualitative measure of stability. It refers to a condition or whether the system is stable or unstable. Next, relative stability. Once the system is found to be stable, it is of interest to determine how stable it is, and this degree of the stability is a measure of relative stability. A relative stability is a quantitative measure of how fast a transient dies out in the system. Relative stability measurement, a relative settling time of each unit or a pair of unit. Relative settling time of complex conjugate pole is inversely proportional to the real part of the roots. Roots or a root or pair of roots move farther away from imaginary axis. The relative stability of the system then improves. Next, we'll discuss about what are the necessity conditions for the stability. There are the two different types of the conditions. First one is all the coefficients of its characteristic equations to be real and have same sign, and none of the coefficients should be 0. However, these conditions are necessary but not sufficient, because it is quite possible that an equation with all its coefficients non-zero and of the same sign may not have all the roots in the left half of the S-plane. Then we'll discuss about Routh stability criteria. The Routh stability criteria is based on the formulating an array, or we can say a table, called a Routh array or the Routh table, using the coefficients of the characteristic equation. The first row of the array consists of the first, third, fifth, etc. dash dash coefficient, and the second row consists of the second, fourth, sixth. In this, it means that first row consists of the odd number of coefficient and the second row consists of the even number of the coefficients. This is the Routh array. If we'll consider the equation, characteristic equation, Q of s is equal to a0 s raised to n plus a1 s raised to n minus 1 dash 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 is equal to 0. Then Routh array is in this way. Here it is. Vertically, there is s raised to n raised to n minus 1, and horizontally a0, a1, then a0, then the a2, a4, a6, even numbers, then a1, a3, a5, odd numbers. Then there is a order of that, whatever the s raised to n minus 1, s raised to n minus 2, like that. After writing that one, a0 and a1, we have to find out the array, that entry, that is b1, b2, b3, c1, c2, c3 up to the an. Very simple formula for finding the b1, b2, c1, c2 like that. Here it is a formula written b1 is equal to a1 into a2 minus a0 into a3 divided by a1. Then the b2 is equal to a1 into a4 minus a0 into a5 divided by a1. In this way we can find out the c1, c2 up to the an. We'll go for example. Here it is, some coefficients are there, and with the help of that we are going to find out the whether the system is unstable or the stable. Then whatever the formula is, whatever the characteristic equation is given, we are going to put it. Then the odd number and even number of the coefficients for s raised to 5 and s raised to 4. Then we have to calculate the b1, b2, c1, c2, then d1, d2, and the final there is a s raised to 0, whatever the coefficient is there. Then here it is, we can say that there are two sign changes in the first column of the Routh array, that 1 to minus 6 and minus 6 to 14. Therefore, this system is an unstable system. Second example, same procedure we are going to follow for this, but here it is what happened in the first column. Not a single sign is of change. Therefore, the system is a stable system. All the first column entries are the positive. The system is a stable system. Next, same here it is, but what happened here, after finding the b1, b2, c1, c2, and all the whatever the unknowns are there, there are four sign changes in the elements of the first column of the Routh array. Hence there are the four roots of the characteristic equation in the right half of the S-plane. Therefore the system is unstable. Then we'll discuss the two different cases with respect to the RH criteria. First case is, first element of any row of the Routh array is a 0. It means that if any row of the Routh array contains only the first element as a 0, we are going to replace it with the one small positive number, that is the infinity, or the small e is there. We'll take the example. Determine the stability of the closed loop. This is the function. Same we are going to by considering the characteristic equation. S raised to 5, 4, 3, 2, 1 and 0 is the coefficient for this raised to 5 is 1, then 2, 3, 6, 5 and 3 is there. Then we'll find out the B1 after using the formula 2 into 3 minus 6 divided by 2, it will come 0. Therefore the first column, first entry is a 0. Here it is a special case. We are going to use the positive number, that is infinity. Here it is infinity. With the help of that positive number, we are going to solve it. Then for the whatever the value infinity tending towards the 0, there will be two sign changes in the first column. Hence the two roots of the characteristic equation means we have to equate it is equal to 0 now to find out the what kind of sign we will get for that. Therefore here it is, sign is going to change. Therefore the system is unstable. Same we are going to do for this also. Here it is, as this tends to the 0, there will be a two sign changes of the first column. Therefore the system is also unstable system. Simple we are going to use first column. Simple example, one sign is going to change, 3 to minus 1.33 and minus 1.32 to 0.5. Therefore the system is unstable. Therefore then we are going to discuss about a second case. All the elements of any row of the Routh array are 0. Means whatever the row entry we will get, that all the rows will be a 0 rows. This condition indicates there are the symmetrically located roots in the S-plane, which may be pair of real roots with opposite sign, pair of conjugate roots on the imaginary axis, complex conjugate roots forming quadratic polynomials whose coefficients are the element above the row of zeros are called auxiliary equations. Order of the auxiliary equations is always even. So we will consider the we'll discuss this with the help of the example. This is the example. Here it is what happened. Whatever the characteristic equation of the transfer function is given, I will consider the characteristic equation. And here it is 1, 7, 6, 42, 8 and 56. I have completed the Routh array. I will find out the B1, B2 and B3. Then C1 and C2. At the time of finding the C1 and C2, here it is, I will consider that 1 into 42 minus 7 into 6 means 42 minus 42 is a 0. Again here it is 1 into 56 and 7 into 8, that is also 0 comes. It means that row is a 0, therefore we are going to use a special case for that. It means that we have to take auxiliary equation of whatever the whatever the row is there, and we have to take the first derivative of that. Here it is, auxiliary equation is s square plus, here it is s square plus 6x plus 8. Therefore here it is d by ds of that is 2s plus 6. Therefore we have to write down here 2 coefficient and the 6 one is there. Then here it is then we have to follow the same procedure. Then all the elements in the first column is positive, so the system is stable system. Same here it is. Then we have to take a auxiliary equation for the whatever the upper, that is a 2s raised to 4 plus 48s raised to 2 minus 50. Take a first derivative, that is 8 and 96. Wherever the 0 comes in the s raised to 3 row, we have to write down 8 and 96 and follow the same procedure. Here it is 8 and 96. Same, find out the b1, b2, c1, whatever. Here it is again one sign get changed. Therefore here it is the system is unstable. Determine the stability of the system. Same procedure. Here it is 0, 0 comes. This is a special case number 2. Take auxiliary equation, take a derivative of that and write down the coefficient for that. The system is stable system. Here it is. With the help of that factors, we can find out whether the system is marginally stable or not. There are the two, if I'll consider that the auxiliary equation and the factorizing the A of S will have s square plus 1 and s square plus 2. Therefore s is equal to plus minus j1, s is equal to plus minus j root over 2. There are two pairs of the non-repeated roots on the imaginary axis. Therefore the system is marginally stable. Then same is there. We have to find out the frequency of oscillations also. Here also we are going to use the case number 2, auxiliary equation, take a derivative of that. After taking derivative of that, here it is s is equal to plus minus j2 is there. So the oscillation frequency is omega is equal to 2 because s is equal to plus minus j omega, comparing omega is equal to 2 radian per second. Then we'll discuss the applications of the Routh array. Here it is. Consider the system with a closed loop transfer function C of s upon R of s. Determine the range of the k. It means that opposite procedure is there. Here it is. We know that the system is stable and we have to find out the one unknown quantity from the characteristic equation. Therefore, the characteristic equation is given s raised to 4 plus 5 s raised to 3 plus 5s square plus 4s plus k is equal to 0. Then we'll prepare array. After preparing the array, one unknown is there, that is the k. Then same procedure, find out b1, b2, c1, c2 and the d is there. Then this, if a system is stable, it means that all the first column entries will be the positive. Therefore, here it is k is greater than the 0 and whatever the entry is there for with respect to the s1 in the first column, that is 84 divided by 5 minus 5k, it is greater than the 0. Why it is greater than 0? Because the system is stable. That means that value will be positive. Then we will simplify that. Therefore, after simplification, we will get a value for the k is 3.36. It means that the system is stable for the whatever the value of the k is 0 less than k is less than 3.36. Means this system is stable for value of the k is in between 0 to 3.36. This is the application of the Routh array. We'll go for another example. Determine the range of the value of the k for this. For the system is stable. S raised to 4 plus 4s cube plus 13s square plus 36s plus k is equal to 0. Prepare Routh array. Again, the system is stable. It means that the value of the k is also positive. Therefore, for the stable system, k is greater than 0 and 36 minus k is greater than 0. Therefore, 36 minus k is greater than 0. K is less than 36. It means that value of the k is in between 0 to 36. The system is stable for the value of the k is in between 0 to 36. 0 less than k less than 36. Thank you.